So we don't have molecular formulas for ionic compounds. I think this might actually be where we left off talking about this. Why can't, do not yell this out. Think about it, jot down your answer. Why can't we have a molecular formula for an ionic compound? Why can't we have a formula that shows exactly how many atoms of each thing are present in that molecule? Jot it down. Why is that not possible? Right, I see a few smirks. People know the answer. They're going, okay. You with the cat that ate the canary grin, why not? There are no molecules in an ionic compound. We talked about this earlier. You can't have you don't have a molecule of an ionic substance. So what we have are these things called formula units, and it just describes the simplest ratio between the positive and negative ions. So we looked at sodium chloride, and that was 1:1. If we had calcium, and, well, we could look at calcium fluoride or calcium chloride. If we have an ion that's got a positive 2 charge, it's going to require 2 -1 ions to balance it out. So we're just looking for positive and negative charges to balance. The simplest way to do that, and we will spend lots more time on this in the next chapter, I guarantee. The simplest way to do that is what we call crisscrossing charges. I'll see if I can write against that dark background and have it show up. So if we have a calcium, which is 2+, and a fluorine, which is 1-, the easiest way to find the numbers of each that we're going to use is crisscrossing those charge numbers. So we now know that we'll have 1 calcium and 2 fluorine. And you'll use that for formula writing. So actually I should probably not put them there, but put them down there, because that's where they'll go in formula writing.
Do you ever have to reduce that?
Yes, sometimes you do. Sometimes you do. And that showed up on the video. Good. So that's how you get that ratio established. Now, we can actually show a Lewis dot diagram for an ionic compound. You've had some practice with drawing ions as Lewis structures. What do you put around an ion to show that it's an ion? You put your brackets and your charge. You can do the same thing for an individual atom. So if we go back to our old friend sodium chloride, there was our Lewis dot diagram for plain old sodium, right? If sodium gives up that valence electron, it's now a sodium ion. And that's how we would show a sodium ion, sodium 1+. So, if we have chlorine, which had looked like that, that's a neutral chlorine atom. If it takes on another electron and it becomes an ion, we now have that. So it took on the additional electron. It's got a -1 charge, and we can show, we can't show a Lewis structure for an ion because there are no covalent bonds. But what we can show is those 2 ions sitting shoulder to shoulder. Not overlapping, not connected, but sitting shoulder to shoulder. Whoops. Okay. So I'd like to ask you to think back to lab B6. That lab you did. If you've got it handy, pull it out. In that lab, you attempted to melt some ionic compounds and some covalently bound compounds, some molecular compounds. You attempted to dissolve them with both water and ethanol. And you looked at whether or not they were conductive. there were some distinct differences that you all noticed. We'll talk about those in a second. So we've got all of these little ions forming a lattice. They form this sort of interlocking structure like we've got on the board with our sodium and chlorine atoms. These charges end up spaced out evenly because you've got what two forces at play? Attraction and repulsion. So the positive ions are attracted to all the negative ions in there and repelled by all the other negative ions. So it's a balance. We can't, remember we had bond energy with molecular substances? In every covalent bond there's some amount of energy. And we talked about things bonding and again balancing what and what. Balancing attraction and repulsion in the covalent bond. But there's actually an amount of energy contained in that bond. And that energy was released when the bond was formed and was required to break the bond. Here, we can't calculate it the same way. So we have what's called lattice energy. And it's the amount of energy that would be released if we took 1 mole of an ionic compound and transferred it from being a solid to a crystalline, from a crystalline solid to a gas. We do not work with lattice energy in here. It's way above the scope of this class. I just want you to be familiar with what it is. Okay, so we've got these positive and negative ions. Fantastic. All sitting shoulder to shoulder. All strongly attracted to one another. Were you able to melt those ionic compounds in your lab? You able to melt salt? No. No, you were not. Matter of fact, they make salt masks. You can buy this for somebody in your life for Christmas or make it. It's a neat present to make. And basically you take rock salt, you sew a bag for it, and you fill it with salt. You can't ever get this thing wet, but you fill it with salt, and then you give it to whoever has stress headaches in your life, and they stick the bag of salt in the microwave, and it retains its heat nicely, and then they put it over their face and they lay down. It's relaxing, so they say. They make rice masks and salt masks.
Sure.
You can do that because sodium chloride melts at what, like 1200 degrees Fahrenheit, 800 Fahrenheit? No, 800 Celsius, 1200 Fahrenheit. Real hot. You're not going to generate that kind of heat in a microwave. They have real high melting temperatures. Why would that be, do you suppose? Jot down any notes, any thoughts you might have on that. While you're jotting, I'm going to pause.